Hi, I'm Nathan.
And I'm Aaron.
And this is our final project for EGR 433 Advanced Computer Engineering. The particular goal of this project was to build and implement a dual-core two-way superscalar computer that could perform a specific set of instructions that is detailed in our report. In this video, we will be going through the different layers of our project, and at the end we will have a quick demonstration. This right here is our outermost layer of our project. It is sort of a top-down view of the outermost perspective. Here we can see the finite state machine at the top, a main clock that represents the stages of fetch, decode, execute, and write back, and here we can see core 1 and core 2. This down here is just a set of displays so that we can manage and observe our outputs. Here at the bottom we have a shared memory block that is used by both cores so that we can read to and write from this register right here depending on the instructions sent to these cores. This priority encoder right here, as well as this OR gate and these inputs over here, are used to prioritize which core gets to write to the shared memory if they were both to get the instruction simultaneously.
Here we have the core of the system. Each core has two pipelines in order to represent the superscalar aspect of the computer. Each pipe receives the fetch, decode, execute, write back clock signals from main, as well as operands and opcodes from the finite state machine, and outputs different things according to the opcode. These also have a general purpose register, which is used to share data between both pipelines, just like the dual cores share read and write data between them.
So let's take a deeper look into each pipe. So here, I'll just zoom out because this is actually a pretty large block. Here we go. Here we have the opcode in pin right here. This is what takes in the opcode that is originally given through main and then fed into the core, which then has two sets of opcodes and operands that is fed into each pipe. The opcode is then sent into this control logic block here, which interprets the information and outputs, depending on the state here, either signals for specific conditions regarding shared memory or GPR, or depending on the state, it may send signals here through these bits to control which function is active, and bits here to control which information is passed into the functional block. This may seem a bit messy over here, but this is used to take in operand data and the GPR data and select which one is passed into these muxes alongside the up and down counters. This is so that we can control when the pipe takes in GPR data or operand data.
Here we have our finite state machine. This basically goes through two different ROMs, each of which controls an entire core. So the clock signal activates this counter right here, which cycles through the instructions in ROM. Each instruction has information for an entire core, both operand and opcode data, and this is divided up between each section and sent back into each individual core.
This is our control logic. I'll zoom out because this is also a pretty large block. This is set up in the same sort of fashion as rail logic, which is a pretty traditional way of showing our information. These 4 bits from the opcode are then separated into bit signals of W, X, Y, and Z, as well as their knots. Depending on the setup here, we used K-maps to determine the simplest way of doing this. We send the signals into different setups of AND gates and OR gates to send resulting signals to our multiplexers, which determine which data is to be used, as well as to our demultiplexer signal, which then tells the functional block what is and isn't the goal of this instruction. Down here at the bottom, we have these very specific instructions that are related to reading and writing to shared memory, either in the core layer to the GPR or in the main layer with the shared memory.
Here we have our function block. This takes in information from both registers as well as a signal from the control logic. The control logic determines where the data goes into which function. So here we have a comparator, an adder, an AND gate, and an OR gate. Each of these outputs to its pipe.
Then just real quick, because we didn't want to have to keep dragging and dropping clocks into our different pipes, we have this setup for clocks. This is an up counter and down counter that we were able to just click and drag as a single block into each pipe. We can control this at a higher level, as we saw with the main. We did the same thing with registers, as you may recall from our earlier discussion in the pipe. Here at the top, it takes in information from the multiplexers, which are used to determine the data that is passed through and latched onto the registers. And then we have a signal that comes in here that is telling this to update. It outputs whatever data is currently in the register out these pins.
Here we have our main clock. This controls every cycle that circuit goes through. We have a main clock over here. It counts from 0 to 3. Each two represent a different fetch, decode, execute, or write back cycle. It sends out a different clock signal out of each of these pins to do different things on each stage in each core.
Alright, now that we've gone through the different layers of our project, let's just do a quick demonstration. So first I'm going to set the up and down counter data, and I'm just going to cycle through the instruction sets. As you will notice at the top, these probes are showing what current data is being passed through. We're just going to keep going through. We can see the comparators here are being activated. We can see, based on these instructions here, that these are being activated. And if we keep going, then what we will see eventually, here we go, with the most recent passive information. One of these cores was told in the previous cycle to write to shared memory, which it has. And now we have data in our shared memory, which proves that our circuit is indeed working. And that is our project. We'd like to thank you for taking the time to watch this video, and we hope that you enjoyed your stay.